I hope everybody is back. We are continuing with the next talk that will be given by Pablo Hermosin from Deimos Space. The title is Low Thrust Sample Return Trajectory Optimization to Thousands of Near-Earth Asteroids Over a Century. So, Pablo, please go on.
Okay, thank you very much for the presentation. Good morning, everyone. And yes, as has been said, I'm Pablo Hermosin, and I work as a mission analysis and navigation engineer in Deimos. And today I'm gonna talk about basically presenting the results of this optimization process we did over thousands of near-Earth asteroids using low thrust sample return trajectories. So let's start first with the problem and the motivation of this analysis. So as you know, the surroundings of the Earth orbit are full of small NEAs that probably in the future could become a reachable source of minerals and water for the planet. So obviously, in order to exploit those resources, we need fast and efficient methods to calculate round-trip trajectories, because I mean we have a lot of asteroids in that zone, so it's important to be able to perform sample return trajectories and have tools that allow us to do that in a very fast way. So for this analysis, we use a synthetic population of more than 4,000 unknown asteroids in order to do the analysis. The term unknown means that we have assumed that we don't know the objects a priori, so we don't know where the objects are, and they are not available or reachable until they are close enough to Earth so it can be detected. And we assume that that detection zone was 0.05 astronomical units from Earth. So until the asteroids doesn't come into that sphere around Earth of 0.05 astronomical units, the asteroids, it's unreachable because basically we would not know that it exists, basically. So as you can imagine, this presents a very big constraint in the design of the trajectory, because obviously things are not as good as you want, and in the optimal launch windows to asteroid doesn't start when the asteroid becomes available. So some of them are very early, some of them are later. So you have to overcome that issue in order to get to the asteroid and obtain feasible trajectories. So let's start a bit with the catalog. As I said, we have more than 4,000 asteroids, and first of all, what we did was to check how many of those asteroids are reachable. And as you see here, the ones that over between 2020 and 2090 are within 0.05 astronomical units are in the order of 3,000. The rest of them, I mean, we analyzed them, and of course, except for some small amount of them in the order of, let's say, around 2,200 or so, that have a very big synodic period and are very far from Earth most of the time. And this number can be increased considerably if we assume 0.1 astronomical units or wherever other measurement that would be adapted to the detection techniques we have in the future, of course. So on the right, you see the number of accessible asteroids per year. Those are, I mean, some of these asteroids come back to Earth every some years. So in this plot, some asteroids are reachable more than once. So we have basically in the order of 60, 70 passages minimum per year, with some years in which we have more than 100 even. So now let's talk about the methodology. In order to find the final low thrust results, we designed a 3-steps method. We started with the definition of the asteroid catalog, of course, and then we did a very first analysis using chemical propulsion, just to obtain the optimal launch windows using chemical propulsion and have an idea of the total delta V of the round-trip mission using this kind of propulsion. Then we use those results to obtain the optimal low thrust trajectories. And so basically we move from the initial guess, we use as an initial guess the results from the chemical and perform and pass that to low thrust trajectories. And finally, once we had some low thrust trajectories, the optimal ones, we included the extra constraints given by the concept of operations. So this, for example, the thing I said before, that you have a maximum distance or minimum distance until you can launch the mission and so on. So we'll be analyzing these steps one by one in this presentation. So starting with the impulsive analysis, and these are the constraints and the conditions of the analysis we did. We started with selecting a maximum mission duration of 5 years. The stay time at the asteroid was 90 days. That is the time considered for this mining process. And since the idea of the mission is, of course, bring back as much as quantity of asteroids as possible in order to exploit the resources, the inbound delta V becomes very important because the inbound mass will be considerably higher than the return trip. So basically the optimization works by trying to optimize as much as possible the inbound and then find the different or the best outbound solution that can be possible, but once the inbound is optimal. So the inbound gets preference with respect to the outbound, and then we just try to find a feasible outbound that fulfills the requirement for the best inbound that we could obtain. In order to do that, we use CESWIC. There is an internal tool developed here in Deimos, in which we can obtain the optimal chemical transfer between two bodies of the solar system. And we can select the start body, in this case is the Earth, the final body, and the asteroid, and in the return mission is the other way around. And the tool uses a search and prune algorithm in order to find all the possible transfers between those objects, taking into account different flybys with different bodies. In this analysis, we stated that the maximum number of flybys was 2, and it could be done with Earth, Venus, and Mars. But since we are very constrained for the maximum mission duration, basically most of the solutions, if not almost all of them, went to the asteroid directly without any flybys, because basically there's no time to perform flybys for the return trip mission with that amount of time. So this slide shows the validation that we perform between CESWIC and the NHAT solution provided by GPL. So in this sample for the 2019 PO1 asteroid, you see that the total mission delta V is very similar for the minimum delta V solution and for the minimum time solution. There are the two types of solution. Also, total mission duration is very, very similar, and the launch date are also very well correlated between those two solutions. So once we were 100% sure that the tool was behaving as we wanted with this set of asteroids, we'd analyze what would be the impact between the sample return mission, that is the one showed here, is a sample return mission with the stay time is only 8 days, and try to determine what's going to be the behavior of the tool when moving to the mining mission, in which the stay time was 90 days. And as I explained before, the inbound solution is not that much change because it still tries to get the optimal inbound, but the outbound is completely changed because it gets less weight in the optimization that the inbound. So that's why the launch date is, as you can see here, in the optimal sample return mission with only 8 days stay time. You're launching in August, and now when you move to mining, you select a launch date 5 months earlier because basically you don't care that much about the inbound with respect to the outbound. And in this case, it's even more extreme because you are launching basically 1 year before. So this was the preliminary analysis we did until we moved to the final solutions of the impulse, so on the chemical analysis, and these are the results we obtained. So you see here in color the 4 delta V's we have, And we have a considerable amount of asteroids with delta V's between even below 2. There are some of them, but between 2 and 4, and more than 1,500 below 6 kilometers per second with a complete round trip solution. Of course, there are some of them that get over 10 kilometers per second, but I mean, this is a way to just prune and determine which were the best population, the best part of the population we could target for the sample return missions. So here is also an interesting plot in which you see the inclination with respect to the ecliptic, the semi-major axis, and the asteroid distribution with the red dots are the ones with lowest delta V. And as you see how the ones with lower delta V are the ones closer to 1 astronomical unit, but there is here a vertical line with a gap. And this is because, as I mentioned in the beginning, there are a considerable amount of asteroids, let's say in the order of some hundreds, in which the synodic period is very big with respect to the Earth. And these are represented by this vertical line gap. That's why those asteroids are basically unreachable for the time span we consider. So that's why there's a vertical line here. So that's the results of the chemical analysis that we basically use as an initial guess and to have an idea of the order of magnitude of delta V we could expect. And now we move to the optimal low thrust trajectories. So initial guess coming from Impulsive. Then here both the arrival and departure be infinite at asteroid and Earth are set to 0. So basically, all the propulsion system is provided by the spacecraft itself. This is a bit conservative because even if we are not considering a launch for this analysis, we are assuming that we can start from L1. And if you can exploit the dynamics of the three-body problem between Earth and Moon and Sun, you can escape the influence of the Earth with some delta V. So the V infinite when escaping the Earth and arriving to the Earth doesn't have to be 0, but it's conservative, assuming that we still need to provide this delta V in this stage of the study. That is a very initial point of the mission, of course. Again, the state time as the asteroid is 90 days. And here's some interesting numbers. The initial inbound mass is 100 tons. So basically, we're assuming that we are carrying back the asteroid to Earth. The initial outbound is 12 tons, from which 7 tons are per propellant. And those high amount of propellant is because we're assuming a water-based propellant system, in which we have a very big thrust for a low thrust propulsion, that is 25 Newton. But the specific impulse is more or less in the order of the chemical propulsion one. So it's a not very efficient propulsion system, but it's based on water. So, I mean, if you are going to an asteroid that it's basically made of water, you are doing that for free. The extra tons you can carry back from Earth are obtained for free. If you're using 30 tons of water in the inbound trajectory, you still have 70 tons of asteroid that you are carrying back using water, basically. So with this analysis, in order to perform this analysis, we use another tool also developed here in Deimos, that is FLOP3. This tool basically solves a boundary value problem coupled with a particle swarm optimizer in order to obtain the global optimum in terms of departure and arrival epochs and infinite velocities, being the final spacecraft mass the objective function. So this is a low fidelity tool in the sense that it takes also into account, it only takes into account the sun as the gravitational force, but that is enough in this stage of the process. And as you see here in this plot in the below, with this, what you want to obtain is where the thrust is going to be applied the most. So you use this as an initial guess solution to a high fidelity tool in which you select where the thrust arcs are going to be, taking into account where the peaks are here in this solution. So the peaks will correspond to the thrust arcs in the high fidelity tool, and the valleys will be basically the coast arcs in the high fidelity tool. So it's just an initial guess. So with this tool, we obtain basically this number of launches per year. So this number of feasible missions, round-trip missions with 5-year duration, 5-year duration period. So it's in the order of 30, 40 for each year. With some years you have almost 50. And if you can launch that many launches every year, you have this accumulated mass at return. It's in tons, so you can bring back to Earth in the order of 1,500 to 2,000 tons per year if you are able to launch those 50 launches per year. So let's see this as reachable resources, not that real resources, because it will depend on the number of launches you have, of course. So these are the results also for the outbound. So you see here that assuming 5 tons of propellant for the outbound, you can reach 60% of the asteroids of the catalog of those almost 3,000 that were already reachable. But if you increase that and the outbound propellant mass up to 7 tons, you can get almost more than 95% of the asteroids reachable. So, of course, this is just let's say a parametric analysis or an initial study, just to determine which are the conditions or requirements that we could face or we would need in order to obtain these results. And as I said before, we are using, in order to do this analysis, we are using a low fidelity tool, or that would be used basically as an initial guess for a high fidelity one. So we have to be sure that the results are representative. And in order to do that, we compare these low fidelity results with the high fidelity ones provided by LOTNAV. That is the one, also a tool developed here in Deimos, in which you can basically take into account all the gravitational forces and also a proper definition of thrust coast arcs in terms of low thrust propulsion. And with this, we obtained these results. We took a sample between LOTNAV and FLOP3 results. And as you can see here, in terms of arrival mass, and the results are very similar. We are in the order of 5% difference, with peaks of 12% and some missions in which with less than 1%. So taking into account, this is a very first study, just to have an idea of the reachable resources we have around Earth. Having around 10% difference it's a very good solution, and the results obtained with FLOP3 can be considered representative. So this is an example of what I was telling before. So you see here on the left the solution provided by FLOP3. So the length of these arrows shows you the intensity of the thrust in that part. So you see here we should have a thrust arc in the beginning, and also a small thrust arc at the end, and basically almost nothing here in the middle. And we move this solution to the high fidelity one. In the difference between them is the order of 3%, which is okay. And you see, I don't know if you can see that very well, but in the red line is the spacecraft line, and the thicker part are the thrust arcs. So it's very well correlated between the two of them. We have a bigger thrust arc here in the beginning, corresponding to these long arrows here. A smaller one, but still considerable here at the end, just to break. And this is represented this last part. And there's also one point here that is, I mean, it's not a DSM because it's low thrust, but it's just a correction in the middle that is representing basically this very low thrust part that we have here. And the rest of it, it's basically coast. So both the final results and the shape and behavior of the tools are in line with what we expected, basically. And finally, also we did the comparison between the low thrust and the impulsive trajectories. So you see here, with this, we just wanted to see if the first analysis using chemical propulsion really made sense as an initial guess. And as you can see, most of the trajectories are around zero. So okay, it's like we can say that this first analysis made sense and helped us a lot in order to obtain initial guesses. And also for a great amount of results, you see how the flexibility of the low thrust, because you can change the trajectory while you are in during the trajectory itself. It's not just small impulses at the beginning and the end, allows you to improve a lot the results of the chemical ones. But as a first glance, doing the chemical analysis help us a lot in order to have representative results or representative intermediate results in terms of delta V in reachable asteroids and so on. So now let's move to the final part of the analysis, which is the inclusion of the constraints, the extra constraints derived for the CONOPS. In this case, we also took advantage of the results we obtained in the first two steps of the analysis, because as I mentioned before, depending on the amount of propellant in the outbound, you could reach a bigger or lower amount of asteroids, and that happened for several parameters. For example, the duration, in which we increased that to 6 years, and this is because, taking into account we are in a very first stage of the analysis for this type of missions, it's always better from our point of view to relax a bit the constraints in order to include as much as solutions as possible that could be reachable. I mean, in the sense that maybe at the end of the day we end up having only 5 years or having 6 tons of propellant, but at this first stage it's better to have the 6 years and 7 tons, and in worst case we can prune these results at the end. So it's important for us to relax the constraint here in order to have the bigger picture, and then we can concentrate in one part if the requirements are changed during the course of or in the future. So how did we deal with these constraints? Basically, the fact that we have to launch not before 14 days after the discovery means that the outbound gains a lot of importance here, because you may be launching, and statistically you won't be launching when you want, but when the asteroid is discovered, and it's not the optimal one. So the outbound gains a lot of importance. In this case, what we did was to select different duration of the outbound, and for those of durations, we analyze different inbound durations. So it's like a search and prune algorithm again. So we created an upper layer in the optimizer in order to orchestrate this. And with this prune and search algorithm, we just basically wanted to explore as many possibilities as we could and select the best end-to-end trajectory that we obtain. So we are still processing some of these results, because this final analysis was done very few weeks ago. But this is a very first set of the first set of solutions. You see how we can basically return to Earth in the order of 40-50 tons of asteroid for each mission. The lowest one are in the order of 30 tons, but we also have some solutions that with 100-ton asteroid in the beginning of the inbound, at the end we have more than 85, like for example this one. So this shows that even if this propellant system is not very efficient, in this particular type of mission is very useful, because basically all the amount of mass you can carry back to Earth is carried back for free. So just to summarize, we showed here how this complete round-trip trajectory optimization method was divided in 3 main steps. And this sequential step allowed us not only to use as initial guesses the results of the previous step, but also to have results from the very beginning, because we've seen that the difference between impulsive and low thrust and the final low thrust are not that different between each other. So from the very first steps, we could already obtain delta V solutions, the duration of missions that could be useful during the process. And according to these results, we confirm that it is possible to perform this round-trip missions to NEAs using this water-based propulsion system, returning in the order on an average of 50 ton for every 100-ton asteroid we get, and in some cases even asteroids or solutions with over 80 ton mass at the return. And that's basically it. Thank you very much. And in case you have any question.
Okay, thank you.